some of the open problems are around. So we know that linear representations of some Metroid exist, but we don't know a polynomial time algorithm to construct them. For example, transversal Metroids, and yeah, there are many other examples. Uh, Another direction was counting and sampling. So counting number of bases in a Metroid. So that problem is so approximately counting. So now that is known with some new results in last few years. But still there are some open problems. So one open problem is to count common bases of Metroid intersection. So in the special case of bipartite matching, it is solved by Jerome Sinclair Vigoda. Okay, so now today I want to talk about this linear programming extension complexity and this online Metroid secretary problem. So, so let me first talk about what I mean. All this area of polyhedral combinatorics. What is it all about? So, um, so there are natural optimization problems on Metroids. So, for example, you can talk about you have weights on the. So, by the way, should I remind what is a Metroid, or I hope everyone knows? So, I had a slide about. Yeah. So, okay. So, I'll remind you later. Um, yeah. So, so for any weighted optimization problem, we can. I mean, for any given weights on the ground set of, I mean, of the elements of the Metroid, you can talk about maximum weight independent set or minimum weight independent set. So this is analogous to minimum weight spanning tree in a graph or maximum weight spanning tree in a graph. Mm, Another, or you can also ask about maximum weight common independent set of two Metroids, which is a generalization of maximum weight matching, right? So these weighted optimization problems, we want to formulate them as a linear program. And so what? So all this theory was built in the 60s and 70s, and what it allowed us to do is to uh, design efficient algorithms for these weighted optimization problems. And so this LP and LP duality, there are different views. So one way to see it is that when you write a linear program for a weighted optimization problem, what it tells you is there is a small certificate for optimality. So whenever you find a optimal solution, you can also produce a small certificate which can be easily verified that this solution is indeed optimal, right? Another way to look at this LP description is that it gives you a combinatorial description of the optimal set, right? So by combinatorial description, I mean um, that. So one way. So for example, consider minimum weight spanning trees. So one way to describe this, the set of minimum weight spanning trees is I can give you the weights and then say consider all minimum weight spanning trees. Now, is there a way to describe this set without giving weights? So I mean, I want the minimum weight spanning trees, but without telling the weights, is there a combinatorial way of describing that set? So is there a, I mean, so basically I want to understand that set of minimum weight spanning trees in a combinatorial way, and this linear programming formulation gives you that a way to understand it combinatorially, right? And then there are these primal dual algorithms based on LP formulations, and these you can view as some kind of reduction from weighted to unweighted, right? So weighted optimization reduces to combinatorial optimization, right? So that's all. I mean that. all this polyhedral combinatorics does for Metroid and Metroid intersection. So, so let's start with. Okay, let me remind you first what is a Metroid. So, so a Metroid is a tuple. So there is a ground set E, and then a collection of subsets I, which are called independent sets. So it should satisfy some axioms, right? These independent sets should satisfy some axioms. So one is it should be independent. It should be the empty set should be independent. Um, Another is that the family of independent sets should be downward closed, meaning if a set is independent, then a subset should also be independent. And for any two sets A, B, for any two independent sets A, B, so I should have written which belong to this its family of independent sets. If B is larger than A, then I can take out one. I mean, I can take one element from the larger set and put it inside the smaller set, such that this A plus B is still independent. So I can extend my smaller independent set by one element, and so this is called the exchange axiom. Okay, and the maximal size, I mean inclusion wise maximal independent sets, they all have the same size and they are called the basis. Okay, so now let's uh, look at the linear programming formulation. So what is our problem? So our optimization problem is we are given some weights on the ground set. uh, so let's say we have some real weights, so one weight for each ground set element. So analogously, in the setting of spanning trees or forests, there we have one weight for each edge, right? And now what we are asking, the problem is we want to find the maximum weight independent sets. So over all independent sets, I want to maximize the weight of the independent set, right? So this weight of set is simply the sum of the weights of the element inside it, right? Similarly, here I could ask that among all forests, right? So F is a forest, and what is the maximum weight of forest? Um, so, I mean, if all weights are positive, then you know that a spanning tree will have a maximum weight. So among spanning trees, what is the maximum weight spanning tree, right? So what we want is we want to formulate uh, this optimization problem as a linear program, right? So how here's how we are going to do it. So can you still see the slides?
Yes.
Okay. Um, okay. So yeah, maybe I'll just okay. Let's see. So so think of every independent set as for every independent set, let me correspondingly let me define a characteristic vector xi, which is in 0, 1 to the e, right? So it represents the set in a natural way that if an element is in the set, I take 1 for the corresponding coordinate. If an element is not in the set, then I take 0. Right? This is a natural way to represent a set by a 0, 1 vector. Right? Now, if I think of W as a vector in r to the e, right? If I think of w as a vector in e-dimensional space, then notice that uh, the dot product uh, of w with this characteristic vector xi is nothing but the weight of the independent set, right? So now what is my uh, problem? The problem is, this optimization problem is, I want to maximize this linear function. Okay, so I want to maximize the linear function w transpose x, where x belongs to this set of characteristic vectors uh, of the independent sets. Okay, so that is the optimization problem. It's exactly the same optimization problem, just expressed it in a different way. So it is still not a linear program. So this is, we are optimizing a linear function over a discrete set of points in this space, right? So we want to convert it to a linear program, or at least a convex program. So the natural way to convert it to a convex program is to um, write the same objective function, but now we will say that x belongs to the convex hull of these uh, characteristic vectors, these characteristic points, right? So each xi is a point in this space, and now we are taking the convex hull of all these points, right? So that gives me a convex set. And now what we should observe is that whether we maximize it over the convex hull or whether we maximize it over the discrete set of points, the answer will be the same, right? Because because our function is a linear function. So right, so we have a discrete set of points. When we are trying to maximize a linear function, it is optimized at the boundary, right? And if you had the convex hull of these points, which is this whole region, and if you maximize the same linear function, you will get the same objective value, same optimal value. So yeah, so now it looks like a convex program, but still it's not a linear program. So I would like to express this convex hull as a, in terms of linear constraints, right? So this is a convex hull of a finite set of points. So it looks like a polytope. So in 2D it's a polygon. In higher dimension it's a polytope, which is a generalization of polygon. So it can be described by a finite set of linear constraints. So what I want is, I want to find that set of linear constraints which describe this uh, polytope. So basically I want to find these, right? So if this is my polytope, then I want to find these bounding hyperplanes, right? So these boundary hyperplanes, the hyperplanes at the boundary, these are the linear inequalities which describe the polytope. So I want to find these, and then it will be a linear program if I describe the convex hull as a set of linear constraints. Okay, so set of linear inequalities. So does it make sense so far? Any questions? So I think I'll need
It's
to
fine.
switch.
Yeah, it's fine.
Yeah, yeah. Yes, I just need to, I don't have empty pages. Yes, I'll just open another. Okay, and so do you see a blank page? What do you see?
Yes, you feel that.
Yeah.
Yeah, okay, thanks. Yeah, so okay, so we have this problem. We want to maximize this over the convex hull of uh, the indicator vectors, indicator points. So let's try to write the constraints, the linear constraints, which will be satisfied this by this convex hull. So first, let us think of linear constraints which will be satisfied by any point in this set, in this discrete set, and then let's try to add constraints so that it is linear constraints which are satisfied by all these points, and then let's see what happens. So these are 0, 1 points, so naturally they all satisfy. So they all satisfy that the coordinates are between 0 and 1, right? So this is for all, oh sorry, between 0 and 1. So this is for all E in E, all elements in the ground set. And then, yeah, so now what more constraints can we add? So, so somehow we need to capture the independence property as in terms of a linear constraint. So we know that, so let's think of in terms of vectors. So let's say we are considering the Matroid represented by a bunch of vectors, right? So if we had v1, v2 till vm, right? And so the independence here is just the linear independence, right? So I want to consider sets which are linearly independent. So I want to write linear constraints such that any linearly independent subset uh, will satisfy that constraint, and any linearly dependent constraint, I mean, hopefully it should not satisfy. Mm, right. So let's first consider any subset. Okay, so let's say we have a subset of the ground set. Now, can we say what is the maximum number of elements we can take from this subset? Right, it's an arbitrary subset of vectors. Uh, and if I'm interested in only linearly independent uh, subsets, then how many I can choose from this set S? So let's say this S is V1, V2 till Vk, right? It's an arbitrary set of vectors. So how many linearly independent vectors can I choose from this? It will be just the rank of these vectors, right? Whatever is the rank of this set, uh, I can choose those many vectors, right? So that means I can write that this summation xc, where I take the sum over all elements in the set S, it should be at most the rank of this set, right? So I cannot, if I'm constructing independent sets, I mean, if I'm interested in independent sets, I cannot choose more than the rank of that set, many elements from that set, right? So does this make sense? Um, and now I add these constraints for all. So I
Yes.
write this constraint for all subsets of the ground set. So for each subset of the ground set, I add this constraint that I can take at most um, rank of S many elements from S, right? So what you can observe now is that any 0 1 vector, any 0 1 vector, if it is if it satisfies the above constraints, uh, if X satisfies the above constraints, then it has to correspond to an independent set. Uh, right, so then X must correspond to some independent set. So that is not hard to see because we are putting this rank constraint for every subset. So by the way, just to remind you, so this rank notion, I mean, when I was talking about vectors, there is a notion of rank, but it naturally generalizes to any Matroid. So for any Matroid, you can talk about rank of a subset. So rank of a subset is simply I mean, the maximum size of maximum size of the independent set inside that set S. So it is exactly analogous to the rank in linear algebra. So you can just yeah, if you think in terms of rank in linear algebra, it's fine, completely fine. Okay.
Uh,
So yeah,
uh,
yeah,
our goal was to just find the I mean linear equations corresponding to this convex polytope. I mean this polytope, right?
right.
We know that this is in mod E dimension, like this all these points
Yeah,
are. Why couldn't
right.
we take all subsets of I mean size mod E and just put the hyperplane like passing through it? I mean there will be some, and we'll have to figure out which side it is. Like I mean,
So
are
you
we
want
minimize the like trying to get a small set of equations which describe this polytope, or just a polynomial size set of equation which describe this polytope?
no, so I'm not worried about the number of constraints. Any whichever way you can describe.
Huh.
Uh,
Uh,
so I didn't get your suggestion. What was your suggestion? How to add linear inequalities?
let's say in R2, if we are
Yeah.
just take every 2 points and we get a line, and we figure out uh, if there is
Hmm.
one side of the point which is solution inside.
Yeah. Yeah,
Uh,
that is correct. Yeah. So in R2, you can just take any 2 points
it will
and
also
connect.
have, it will also get some middle to, I mean, it,
Right. So for example, this line is not a valid inequality
and
because
that, yeah,
there are points on both sides, but you can check that. You can check that all points are on one side. So
yeah,
those are precisely the inequalities. Yeah, that is correct. Um, so in higher dimension, we need to consider hyperplanes.
yeah,
We need to take, I think, e many points and then see if every other point is on one side of that hyperplane.
yeah,
So, but I mean, how to do that? I mean, how to do that process? So we'll have to list down all these points corresponding to independent sets. And if we do this process, it turns out that the hyperplanes are precisely these. This is the precise description of the that corresponding convex hull. So this I have one linear inequality for each subset of the ground set.
yeah.
Yeah. So
Thank you.
these are exponentially many constraints, and which is not unusual. Um, so you can easily imagine that you have a subset of you have a set of points such that if you want to write down the linear constraints bounding the convex hull, you will need exponentially many linear constraints. So that's what also happens here.
Thank you.
Yeah. Okay. So then, yeah. So then this is the um, this is a so it turns out. So I only showed you here. My claim was only that if any 0, 1 point satisfies the above constraint, it's an independent set. That is not good enough, right? I need to show that any point, even not necessarily a 0, 1 point, any point. So, for example, what could have happened is the picture could have looked like. Uh, so these are my points, and it could. I mean, these inequalities. For now, my claim is only that all points satisfy, all 0, 1 points satisfy the inequalities. So the picture could have looked like this: that I got some linear constraints, I got some hyperplanes such that these points are inside the convex hull, inside the polytope described by the linear inequalities. But then I will have, uh, if this was the situation, then I would have some points outside the convex hull of the given points, right? But it turns out that this is not the case. That these constraints precisely describe the uh, convex hull. So these constraints do not look like this. They are precisely, they look like uh, they are here at the boundary. So there are no additional points we are getting. So every point, yeah, so let me write it as a claim. Yeah. So every point, so this is, so any point in RE satisfying the above constraints, um, we can say that it is in the convex hull of the independent set points. Um, so in other words, it's a convex combination of some independent set points, right? So it is inside the convex hull of these characteristic points of the independent set. So this is a non-trivial claim. So this requires a proof. So it's not very hard. It can be proved using. So, for example, one way to prove it could be to use the exchange axiom, right? Or I mean, the fact that the greedy algorithm works, right? So we know that using the exchange axiom, we can show that the greedy algorithm for optimization works, and that can be used to prove that this fact that the constraints, the linear constraints, describe the convex hull precisely. Um, okay, so once we know that, then we can say that if we know this, then we can say that if we maximize any objective function over, yeah, something is, yeah, if we maximize any linear objective function over these constraints, um, so by the way, I don't need this less than equal to 1. This less than equal to 1 is actually implied by the other constraints. So when I write these constraints that for every s, xc is at most rs. So in particular for a singleton set, it implies that um, each Um, yeah, each coordinate is at most 1. So this is for all subset. So when I do this, when I'm optimize this linear function over these constraints, the maximum value I will get will be exactly the maximum weight of an independent set. And that happens because we have, I mean, I'm claiming that these constraints describe the convex hull of independent sets precisely. Um, yeah. So, yeah. So, any questions on this? So, how is this useful? So, once you get this linear programming description, then it also gives you a way to design optimization algorithms. So, for Metroids, we know that greedy algorithm works for the optimization, right? Just sort the elements in increasing order of weights or decreasing order of weights, and keep picking elements as long as you have independent sets. So that algorithm is simple. But for example, for Metroid intersection, uh, the optimization algorithm is not so simple. And this linear programming description, if we can find a linear programming description for Metroid intersection, then that would help us in designing a algorithm for optimization, right? So let's talk about the linear program for Metroid intersection. So, I mean, there is an amazing result of Edmonds. So, what is Metroid intersection? Let me remind you. So, we have two Metroids. So, we have a Metroid M1 on ground set E and some independent sets, family of independent set I1, and we have another Metroid M2 on the same ground set and some other family of independent sets, right? So, for example, you can think of M1 as the graphic Metroid where independent sets are forests, right? And M2 as another Metroid, let's say partition Metroid, where we partition the ground set into a bunch of blocks. And for each block, I have a cardinality constraint. So I say at most K1 element from the first block, at most K2 element from the second block, right? So that's a partition Metroid, and so on. So when you put these two together, then I'm asking for a forest you can think of this partition Metroid as some colors. So each block is a color. So I'm saying give me a forest which has at most K1 blue edges, at most K2 red edges, at most K3 green edges, and so on. Right? So so the graph is given and the colors are also given as part of the input. And also these numbers are given as part of the inputs. Right? So this is a typical problem in Metroid intersection. And now we are wondering whether we can write a linear program for such optimization problems. So we can also have weights and we can ask for maximum weight forest satisfying these cardinality constraints, right? So that's an example. So amazingly, turns out that you don't have to do much work for writing a linear program for um, Metroid intersection. So okay, so first let's see why it's a non-trivial task. So so let's say these blue points are the independent sets uh, of the Metroid one, and let's say the red points are the independent sets of the um, of the Metroid 2, and then what are the common independent sets? The common are which are both red and blue. So I don't know if you can see it, but these 4 points are supposed to be both red and blue. Okay, so these are the common independent sets, and interested in the convex hull of these. And so one attempt could be I just consider the linear program for both the Metroids, right? So and just put them together, right? Just put the linear constraints together. That would be the natural approach. So for the first Metroid, the linear constraints are these, right? So that gives me this polytope. And for the red one, I will get uh, these as the linear constraints. And when I put the linear constraints together, what I get is the intersection of the convex hull. So the question is the intersection of the convex hull is same as the convex hull of the intersection? Okay, so yeah, I think I need another picture to show that it is not always true. Oh,
And by the way, is XE less or equal to 1 not required? Oh, it is here you have written. Okay.
yeah, but
Is it not required?
yeah, it's not required because the second constraint implies this. So when
Oh,
I write this constraint for a singleton set, it will say that, right,
okay.
that yeah, that a coordinate is at most the rank of that singleton set, which is at most one.
But are all singleton sets independent?
No, they need not be, but their rank will be at most one, right? Their rank cannot be two.
Yes. Okay.
So the rank is either one or zero,
Okay.
which is fine. Yeah. Yeah. So yeah, somehow the order of the pages is okay. So we are talking about two Metroids. Okay. So we have yeah, we have M1 and M2. And yeah, so my point was that um, if I take two polytopes, right? So this is the convex hull of the red points, and now this is the convex hull of the blue point. So let's say these 2 points are both red and blue, right? So yeah, so what are the common points? The common points are let me circle them. Right, these are the common points, red and blue. So if I just intersect the convex hull of blue points and the red points, I get this whole region, right? This whole region is the intersection of the convex hulls. But finally, what am I interested in? I'm interested in the convex hull of the common points, right? So there are only two common points, and their convex hull is this green line, right? So in general, if you just put the linear constraints together, that will mean you are taking the intersection of the convex hulls. But like this picture shows, that the intersection of the convex hulls is not the same as the convex hull of the intersection points. So, but it turns out in the Metroid intersection world, they are equal. So that is an amazing result. So let me write it what I'm saying. Um, so if I take the convex hull of all the points which are which common, so it is also independent in I1, it is also independent in I2, right? So in that example it would be a point, it's a forest which also satisfies the cardinality constraints, right? Now this is the same as the intersection of, if I take the convex hull of uh, just the independent sets in the first matroid and the convex hull of the points in the independent points corresponding to the independent sets of the second matroid, right? Right, so this is the convex hull of all the forest points, and this is the convex hull of all the points which satisfy the cardinality constraints. And if I just take the intersection of the convex hull, it turns out that it gives me precisely the convex hull of common independent sets. So this, as this picture shows, this does not happen in general, but magically it happens in the um, setting of Metroid intersection, and that you can say that is somehow that it is the reason why Metroid intersection is tractable, why we have efficient algorithms for Metroid intersection.
So Rohit,
Yeah.
so if you have say three Metroids and then try to consider their intersection, then also this can be extended.
No, with three Metroids this will fail. This theorem does not hold for three Metroids. Okay, so then the linear program we will write for Metroid intersection will be simply um, so we have this, and then we have the rank constraints R1s. So now R1 is the rank of the first Metroid and R2 is the rank of the second Metroid. So we just put the constraints together and that's all. That's the set of linear constraints describing the intersection. Yeah, and we can also write the optimizing function. So that is the linear program describing Metroid intersection. Okay, so yeah, maybe let me talk about this as an example. Let me talk about this colored forest, right? So let's say we have a, yeah, so please let me know if there are any questions. Okay, so let's say we have this graph and there are colors on edges. So for simplicity, let's say there are only three colors, red, blue, and green. And we want to find the maximum weight forest, which has at most K1 red edges, at most K2 blue edges, and at most K3 green edges. Also, and so weights are also part of the input, right? So this is the input, graph, weights, and colors. So now to solve this rainbow forest problem, I will write the following linear program. So I will maximize double transpose X. Then first let us write the coloring constraints as linear constraints. So we can write for all red edges, right? For the red edges, the sum should be at most K1. So that enforces that I can take at most K1 red edges. Similarly, I write for blue and green. Okay, so I'm not writing it. We can write for blue and green, similar constraints. Now, what about the forest constraint? So how to express the forest constraint as a linear constraint? So, so for any set of edges, so consider any set of edges. So for any subset of edges, how many maximum number of edges can we take from that set? So can we say something? Mm, so in Metroid terms, it is the rank of that set. But what is the rank in the case of forest? So if I take an arbitrary set of edges, what is the largest size of the forest in that subset?
Number of vertices minus one.
So that is if your graph is connected, then it is v minus 1. If your graph is a bunch of connected components, then it is number of vertices minus the number of components, right? So which is precisely the rank. So what I can write here is uh, the number of vertices minus the connected components, number of connected components in, if I just consider these edges in S, right? So forget about other edges, just consider the edges in the set S, then it will form some connected components. So what is that number of connected components, right? So you just subtract that from V. So this is the rank. This is the rank function of the graphic Metroid, because this is precisely the maximum size of the forest inside S. So I hope I'm not missing a plus one. Yeah,
It's correct.
yeah. Thanks. So that's the magic of this Edmonds theorem, that you can just put these two constraints together, the colored constraints and this uh, forest constraints, and then it just works out. Okay, so I think that's all I will say about the polyhedral combinatorics. So the motivation for all this is that it leads you to design algorithms, right? All this polyhedral theory you can use to design all kinds of algorithms, not just uh, sequential optimization algorithms, but also um, so yeah, there are a few results in parallel algorithms where you need this polyhedral theory, because as I was saying that once you write this linear programming description, it also gives you a combinatorial description of the optimizing set. So if I'm looking at the maximum weight forest satisfying these colored constraints, there is a way to describe it combinatorially without talking about weights. And basically this polyhedral theory gives you that, and that is useful in designing algorithms. So now I think I will come to some open problems. uh, yeah. So Amit, how much time should I take?
So this meeting is till 1:30. You can take say until 1:15 should be fine. Or is
Yeah,
1:20?
yeah, okay. So I'm switching off my video. So my battery, yeah, I don't have a charger and the battery can go down. So probably it will not survive for till 1:30. Uh, okay, so let me quickly talk about what is called linear programming extensions. So in this um, what is this all about? So this is about reducing the number of constraints using a few extra variables. So as we saw, the number of constraints we wrote for uh, Metroid, that there were exponentially many constraints. Um, uh, and also that the same thing happened for the forest. For the forest polytope, we had exponentially many constraints. So the question is, can we reduce the number of constraints? Still describe this. I mean, the linear program should not change, right? It should still describe the same thing, and uh, but we are allowed to use few additional variables, because without additional variables, you can show that. I mean, you can easily construct examples where you cannot reduce number of constraints, right? You have to have exponentially many constraints. Okay, so how can you reduce number of constraints using additional variables? So very simple example, let me give. So let's say I have these constraints: x1 less than equal to y1, x1 less than equal to y2, x1 less than equal to y3. So I have six constraints like this, right? So if these are six constraints, if I use an additional variable z, then I can describe the same feasible region, the same feasible region using only five constraints. So on the right hand side, you see that I have used only five constraints. So from six, I went to five, and you can verify that um, the set of xy points which satisfy the constraints on the left, um, they are same. Essentially, they are same. I mean, they are the same. But on the right hand side, I have to say that for a set of xy points, there exists z satisfying these constraints. So it's an easy exercise to show this. So that's how we can reduce number of constraints using additional variables. So then we can ask for Metroids, can we uh, use additional variables and reduce the number of constraints in the Metroid, in the linear program for Metroids or Metroid intersection? So, there are many interesting results known here. So for special Metroids, we can write. So for example, in the graphic Metroid, so this is the maximum size forest setting, right? So for graphic Metroid, from exponentially many constraints, you can bring it down to, I think, something like number of vertices times number of edges. These many constraints and these many variables. So originally you have number of variables is the number of edges, right? You have one variable for each edge, but then you introduce so many new variables, and then it helps you bring down the number of constraints to this much. Similarly, for transversal Metroid, you can do this. You can come down to a polynomial. Let me just say poly uh, in poly in the input size, in the ground set size, right? So this is possible for these two Metroids, and it's possible to do this for many Metroids, not just these two. Okay. Uh, so what is also known is it is impossible to do this for all Metroids. So this is some kind of counting argument that uh, I cannot uh, because there are too many Metroids. There are W exponentially Metroids on ground set size M. Uh, so one has to appropriately argue that we cannot write a small linear program for all Metroids. So we will need exponentially many constraints. But for special Metroids, we can hope, right? For special Metroids which are explicit, right? So a graphic Metroid is given by a graph. Transversal Metroid is given by a graph. For such explicit Metroids, we can hope for a small linear program. So yeah, I could have shown you the small linear program for one of these. Um
So,
Okay.
question in
Hmm.
the previous slide, like just above this converting by
Yeah.
six to five equation.
Yeah. Yeah.
So here, if we consider, I mean, some polytope where the number of constraint is like somehow tight, meaning like it's exactly the boundary hyperplanes equation. We don't have some redundant equation. Can we still
Yeah.
like reducing the number of constraint by somehow increasing the number of? Can we still do it? Is it just saying that we don't have any redundant constraint, or is it more than that? Like,
No, no, it is much more than that. So in this example, on the left hand side, there is no redundant constraint. Oh, sorry. So this three was two actually. Yeah, sorry. Yeah, so these were actually tight. There was no redundancy here, but still using an additional variable, I could reduce the number of constraints. So that's not simply throwing away redundant constraints. Um, yeah, I don't know how else to say it.
no, no, I mean, the left one is in two dimensions, right? X1 and X2 are the only variables.
Right, right, right.
I
So
could
I'm
just
going to higher dimension. Yeah.
I could just replace it by x1 is lesser than or equal to minimum of y1, y2, y3, and same as x2. Like it will come down
Ah,
to
but that's not a linear constraint if you say minimum of y1, y2, y3.
yeah, but I know y1, y2, they're constants. Okay.
No, no, no. This when I write these constraints, I mean all points xy in R2 which satisfy these constraints,
Oh,
subject to these constraints, right? So that's what I mean.
so-
So there is no value for y1, y2, y3. It describes polygon. It describes a polygon in two, three, five dimensions, right? So this is five dimensional world.
oh,
Uh, yeah, yeah. Oh, okay. I think I got the confusion. So this y1, y2, y3 was on the right hand side, but I meant that these are variables. I did
okay,
not mean that they are constants.
okay, okay.
Yeah. Similarly, here I'm working in six dimensions. So I have six variables here. So x1, x2, y1, y2, y3, z. These are six variables. Yeah. So I increase the number of variables and I reduce the number of constraints. So there is a very cool geometric object which
Right.
shows this. Um, so what we can so if we consider a pyramid where the two triangular faces are not parallel to each other. Okay, so I don't know if it looks like a pyramid, but yeah, I hope it. This is
Uh,
supposed to be a 3D object. Okay, uh, so it's a pyramid with triangles are not parallel to each other,
mhm.
uh, and then if you project it on 2D, you will get a hexagon. So what it means, so in 2D you have six constraints,
Yeah.
but when you go to 3D, you have only five faces, right?
Oh, I see. Nice.
So
Okay.
right, so from six you can go to five when you yes from 2D when you go to 3D. So that's what is happening.
Nice.
So you can see that in this, as long as we are in the 2D, the six constraints are necessary, right? They are all tight. We cannot remove anything.
Yeah.
Yeah. So that's how we can reduce the number of constraints.
Okay.
So this, yeah, it is a inverse of projection basically. So this down operation was projection. I just did the opposite of projection. This is called the extension. Okay. So
Right.
yeah.
And finding this extension, like I mean, if I ask, does there exist an extension of such in is that doable? I mean, solvable? Like, I give you some. I mean,
So, yeah. So it is. I mean, it is in the flavor of uh, like we ask, is there a small circuit for this polynomial, or is there a small Boolean circuit for this Boolean function? So it is of that flavor. So so there is a characterization in terms of something called non-negative rank of the Slack matrix, but it doesn't. It's not an algorithm. So in W exponential time, I guess you can do it.
Okay.
But yeah, no, in not doubly exponential time. So you can do it in polynomial time in number of constraints. No, no, no. Yeah, I think doubly exponential time. Yeah,
Okay.
yeah.
Okay.
Um, yes. Okay, so now I just want to mention a few open problems. So as I was saying that for graphic Metroid and transversal Metroid, we know some small linear programs. So maybe for transversal Metroid, I will write that linear program. And yeah, maybe let me first do that. So that will give some idea how uh, we can reduce the number of constraints. So transversal Metroid is what? We are given a bipartite graph, and bipartite graph, one side is larger, one another side is smaller. So the larger side is the ground set. Okay, so this is E. The larger side is the ground set, and so recall that we say that any subset is independent if I is perfectly matchable to the right hand side. Right, so that's the definition of the transversal Metroid. Okay? So I hope the definition is clear. So now, when you write the Metroid polytope, the linear constraints, uh, just follow the what we had done with the rank. Then this is what you get. You get for every, so here E is an index for a vertex on the left hand side. So I hope that is not confusing. So my ground set is this set of left hand side vertices, and then what we write is that for any subset, uh, um, yeah, so I think it's not easy to write the rank, but there is a different way to write it. Yeah, so this I can say is at most the number of neighbors. So the number of neighbors is not the rank, but it's still okay. The number of neighbors is still an upper bound on, right? If you have only three neighbors, then you can match only three nodes from the set S, right? If set S has three neighbors, so in this example, it is only two neighbors. So then I can only match two of these, right? So that's why I can write this, that this sum is at most the number of neighbors. Uh, so again, S is a set of vertices. Um, so, and I think, yeah, we should also add that every XC is at most one. So, yeah, so this is for all E and this is for all subsets. So this is an exponential size program, and I want to see if we can write a program with polynomially many constraints. Um, so here is a way to do it. So we'll introduce, ooh, yeah. So yes, so I will introduce. Um, so let me call the right hand side vertices as U, right? And I will introduce variables for every edge. So for an edge E comma U, if this is an edge, I will introduce a variable, let's call it y E comma U, right? So this is the edge variable for the edge connecting E on the left hand side and U on the right hand side. Right? Basically, I will write the matching linear program. So I will say that uh, um, I can take so first of all, these are all non-zero, right? For all edges, I write this that these are non-zero variables. Then for every vertex U, uh, if I take the sum over all neighbors of U, right? All edges incident on U, this sum should be at most 1, right? So here, yeah, I mean over all left hand side vertices which are connected to U, which have an edge to U. So, so for every vertex, I'm just taking the sum of the edges incident on it. That should be at most 1. Um, right. I think that's it. And then I can say that um, the left hand side variable xc cannot be um more than the vertices incident on it, the edges incident on that vertex, right? So if so, basically this is counting the matching edges. Um, no, I think I need to write. Yeah, I'm a bit confused. So this is the sum over all u's which are neighbors of this vertex E. I should write it is. Yeah, I think I should write this. Yeah, yeah, maybe there is some error, but roughly this is the idea. I write the program, I introduce edge variables, I write the linear program for matching, and it turns out that if I project it, right, if I project it down to the x variables, the original variables, it is precisely uh, this polytope. Uh, so yeah, so I think yeah, I think it's easy to verify that all these constraints in the original linear program, they are implied by the constraints I wrote here. So that's how you can write a small linear program for transversal Metroid. Graphic Metroid is somewhat similar because for graphic Metroid also we have this that the number of edges from, like, if I have k vertices, I can take at most k minus 1 edges from it, right? So so it's similar to this matching, but it's not exactly the same. There is a minus 1 there, but it's yeah, so you have to do some tricks and then it works out. So then let me come to the open questions and then I'll conclude. So I have another set of slides. Yeah, so yeah, basically the open problems are, so one problem you can ask is to improve the linear programming size for graphic Metroid or transversal Metroid.
Hey,
And
Rohit,
yeah,
Rohit, you
yeah,
cannot see the new slide.
yeah, I'm not showing any slides now.
Okay.
So yeah, uh, yeah, maybe now you can see. Yeah, so as I was saying, some small linear programs are known for graphic Metroid, transversal Metroid, and many other Metroids. So the open questions are about many other explicit Metroids are there for which we can hope that there is a small linear program, but we don't know how to write it. Um, Also, other open problems are when we do these Metroid operations. So I had talked about generating one Metroid from another Metroid using some operations like deletion, truncation, uh, contraction, projections, lifts. So all these operations, what happens to the linear program? Can we, if we have a small linear program for one Metroid and we do some operation like Dilbert truncation, and we get a new Metroid, can we still have a small linear program for the new Metroid? So yeah, you can find more such open questions on this blog, Metroid Union. Um, yeah, and as I was saying that for all Metroids, you cannot hope to get a small linear program. So in fact, for almost all Metroids, you need exponential size. Yeah, so that's all I think I have.
One question is like what happen if you take the dual Metroid, then the linear program would be easy to construct, right? Like the I have the
Yeah, so for dual Metroid, yeah, it's easy to construct the linear program if you have the for the original Metroid. Yeah,
and for linear Metroid, the linear program is
yeah. So that's a really good question. So we don't know if there is a small linear program for all linearly representable Metroids. We know for some like we know something called regular Metroids. We know, but for example, a good question is any Metroid representable over F2, finite field of size 2. Can we get a small linear program? So this is completely open, I think.
oh,
Yeah, but yeah, there is no reason to not have a small linear program. I mean, I don't know of any reason. Yep.
any other question from okay, thank you, Rohit. So,
Okay. Okay. Thanks.
so I'll share the recording with you.
Yeah. Sure. Thanks.